Okay, so let's say that we have a Cartesian plane, and on our Cartesian plane, we are going to plot a linear line. So, for example, we will plot it in red, and we will say that y is some function of x, and in this case, it's going to be 2x. That's going to be our linear line, and it's going to look something like this, right? And we are asked to find the gradient or the slope of this line. Well, from linear algebra, we know that the general equation for a linear equation is y is equal to mx plus c. And if we liken this to our equation, the 2x, we can see that in our case, m is equal to 2 and c is equal to 0. And we know that the gradient is equal to the value for m. So we can say that the gradient is equal to 2. But what if we wanted to go about this another way? Well, we could say that we could take 2 points, right? So let's label these points. Here we can have the point 2, 4, and up here we'll take the point 6, 12, okay? And we're going to use these 2 points to find our gradient instead. Well, what we're doing here is we're saying that the gradient, we know that gradient is equal to rise over run. And what is the rise? Well, the rise is this change in our y value, how far we've come up the y-axis. So we're going to use a symbol called delta. It's the triangle. Change in y, delta means change, so change in y divided by the run, which is the change in x. It's how far we've come along the x-axis. And we know that this is equal to, well, we've gone from 4 as a y value at our first point, and we've climbed up to 12. So the difference is 12 minus 4, which is 8. And for the x, we've gone from an x value of 2 up to an x value of 6. So 6 take away 2, which is 4. And 8 divided by 4 is 2. So the gradient is 2. We have got the same solution, doing it 2 different ways. But what we're going to focus on for today's topic of differentiation is the second way of finding a gradient. And the reason being is because what if we are asked to find the gradient of a function that doesn't have a constant gradient like a linear line? Okay, if we go back here, it doesn't matter what point we take along this linear line, the gradient is always 2. But what if we go down to this Cartesian plane, and I plot a function of x, which is equal to, say, a quadratic, a parabola, x squared. And it has, we'll draw the function in red, it has this sort of shape to it, right? Well, how are we going to find the gradient of that? Well, to start off with, let's have a go at doing it the way that we did the linear line up the top here. So let's take 2 points. So we'll take this point here, and we'll call this point when x is 3, so 3, 9. And we'll take this point down the bottom here, we'll say this is when x equals 1, and we have the point 1, 1. Okay? And we are asked to find the gradient. Well, if we do it the same way that we did that linear equation, we say that the gradient is equal to the rise over the run, which is the change in y divided by the change in x. Well, if we're doing the change in y divided by the change in x, we actually form this triangle in blue, the same way we did with the linear equation. And what we're really finding is we're finding the gradient of this blue line here, not this red line. So we have all of this space in green, which is an error. Okay, that's sort of like our error region. So what can we do about this problem? Well, what we do is we make the triangle that we've got there in blue as small as we possibly can. Okay, so instead of making it super big, we're going to make it absolutely as small as we can, even smaller than what I draw it now. Okay, so instead we make a triangle like that. So we take the x value at this point and the x value at this point, and we try and make those arrows as close as we possibly can so that the blue linear line lines up almost exactly on top of that red line, and there's no room for that green shaded region. Okay, so what we're going to say is I'm going to say that this blue arrow here is, of course, just our value for x. And this blue arrow is x plus h. Okay? And that would mean that this point here would be the function of x. And this point here would be the function of x plus h. Okay? And in this case, now that we've made our triangle so small that the linear line lies on top of the quadratic line, we can now use this formula. We can use the gradient equals rise over run because the lines are on top of each other. They're going to be the same. So the change in y, well, that is the same way we did the linear one. It's going to be f of x plus h, take away f of x. And the change in x is going to be x plus h, take away x. Right? X plus h is the second point, x is the first point. So we can simplify that down to, we'll do underneath, we can simplify that down to f of x plus h, take f of x. And on the bottom here, x plus h, take away an x, that's just going to give us h. And that makes sense, right? Because this length in here is going to be h long. Okay? But how can we make it so that this formula is agreeing with the fact that we're making our triangle as small as we can? Well, we want to bring the blue arrows. We said that we want to bring these blue arrows as close together as we can, which means we want to shrink the length of h. Okay, so we want to make h as small as we can. In fact, we're going to make it so small that it's going to get as close to 0 as possible. And we're going to denote this by saying we're going to take the limit as h moves closer to 0 of our equation that we've just come up with. So as h moves to 0, that is basically our way of mathematically writing the triangle gets smaller and smaller and smaller until the linear triangle line lies exactly on top of the quadratic line. So now that we have our formula here, we'll highlight this formula in blue because this is going to be important. Okay, and we also have our specific function. We can start plotting in some values, making some substitutions here. So we will say the limit as h moves to 0. And now what is f of x plus h? Well, if f of x is equal to x squared, then f of x plus h is going to be x plus h squared, right? And we're going to take away, we just said that f of x is x squared, and we'll divide by h. And let's now expand out that top bracket. We end up with x squared plus 2hx plus h squared, and we take away the x squared that's left over there, divide by h. Well, we can see a simplification here that this x squared and this minus x squared are going to cancel each other out. So let's do that. We end up with the limit as h moves towards 0 of 2hx plus h squared on top of h. And let's just give ourselves a little bit more room here. What we can see now is we could take out a common factor of h on that numerator, right? So if we do that, we'll be able to cancel that h as a denominator out. So if we bring a h out on the top, we end up with 2x plus h, divide by h, and these h's are going to cancel. And what you might be thinking is you're thinking, oh no, we can't do that because we would be dividing by 0. But we're not dividing by 0. Remember, h is never actually going to get to 0. It's just getting as close and close and close as we can. So it'll be like 0.0001 divided by 0.0001. That will still give us 1. That won't give us an error. So this will now give us the limit as h tends towards 0 of 2x plus h. Well, as h becomes so small that it's going to become negligible. If we have, 6 and we add on top 0.0000 with a million zeros and a 1 on the end, it's still going to be pretty damn close to 6, right? So we can just write this as 2x. So our gradient, our solution now is 2x. But what does that mean? Okay, so that I can zoom in a bit, we're going to write that our solution was the gradient is equal to 2x. Okay, let's come over here. What does that mean? Well, it means that at different points, the gradients are going to have different values, which makes sense, right? So if we use orange and we take our point 3, 9, okay, the gradient is when x is equal to 3, it's going to be 2 lots of x, so 2 lots of 3, which is 6. Well, if we take a point in between, say this point in here, when x is equal to 2, okay, so slightly further downwards, we get gradient is equal to 2 lots of 2, which is equal to 4. Okay, and if we take that point that we had just over here, the 1, 1, gradient is 1 lot of x is 1 in this case, 1 lot of 1, which is 1. And this makes sense, right? So it's saying the further we move up this line, up this quadratic curve, the steeper the gradient is getting. When x is 3, the gradient is 6, and that's much bigger than when x is 1 and the gradient is only 1. And that makes sense looking at it, right? So that's how we can use this magic formula that we highlighted in blue over here, okay, to find the gradient of functions that aren't linear. So it might be, the function is x squared, or the function is 4x cubed, or something like that. This formula will always work. But what now if I told you that really, yes, you will need to know that, and it's important to understand it, but there's actually a shortcut to just go straight from x squared to 2x. Okay, so let's have a look at that. Well, if we come in over here, I'm going to create a bit of a table, okay? And we're going to say that we're going to have whatever the function of x is, and then we're going to say, I'll tell you what the derivative is, and then we're going to make some notes or any observations that we see. Okay, so let's build our table, and let's take some functions of x. Let's go with 4x cubed, and 2x squared, and 6x, and 4. Okay, let's have a look at those functions of x, and I'm going to tell you what these derivatives are, okay, because I know the little trick. So I'm going to use the little trick that I know, and I'm going to say that this derivative is 12x squared, this derivative is 4x, this derivative is 6, and this derivative is 0. Another way you could find these functions of these derivatives is to use this formula, right? We can use this formula in here to find the, we can use, for 4x cubed, we can put that into this formula, and we will come out with 12x squared. So you can use these to practice and see if you can get to the right answers by using that formula there in the blue. But for now, let's have a look and see if there are any observations that we can pick up. Well, I'm going to use a highlighter. We'll use a blue highlighter. This 12 here is a product of 4 multiplied by 3, right? And this 4 here is a product of this 2 multiplied by this 2. And another way we can write 6x is 6x to the power of 1. So we would end up with this 6 is a product of this 6 and this 1, right? And what's anything to the power of 0? Anything to the power of 0 is 1. So we can write this 4 as 4x to the power of 0, or 4 times 1, which just stays at 4. So we're not changing that. And this 0 is a product of 4 and 0. So there's an interesting pattern going on there, right? There's one more pattern that we need to have a look at. And that is that we can let's write this as 4x to the power of 1, and this is 6x to the power of 0, okay? And this can be, x to the minus 1. Well, if we use yellow this time, we can see that this 2 is 1 less than this 3. And this 1 is 1 less than this 2. And this 0 is 1 less than this 1. And this minus 1, which, it's just 0, this minus 1 is 1 less than the 0. So, our notes and observations are, if we have a general formula for f of x, so if f of x is equal to some constant, let's let it be a, and we're multiplying obviously by x to the power of some number, n, then the derivative is going to be the product of a and n, okay, the bits that we highlighted both in blue over here. So that would be a, and that would be our n, and we're timesing those together to get our derivative out the front there. We're going to get an as the new constant, and then we get the x to the power of 1 less than whatever the n was. So this 2 is 1 less than this 3, and this 1 is 1 less than this 2. So x to the power of n take away 1. So, for example, one extra example, if f of x is equal to 3x squared, then the derivative is going to be, well, this is a equals 3, n equals 2. So we put it into this formula here. 3 times by 2 is 6, x, and then the n was 2, so n take 1 is just going to be 1. And of course, x to the power of 1 is just x, so the derivative is 6x. Okay? So, attached to this video, I will leave you the solutions and the questions to be able to do this conversion here. So putting all of these in this column here into this formula and being able to get the correct derivative. And then we'll also have a couple of questions and the solutions on how to do this shortcut method as well. And that's pretty much it for how to do differentiation. Okay, there's 2 bits there that you need to know before we move on. Alright, thank you very much.